Okay guys, our next lecture will be based on the design of built-up columns. First coming to the question, what is the need of a built-up column? In the beam section, we have also see there are need of a built-up beam. When if the load is high and the depth of the section is specified. In case of beam, then we needed the built-up beams. In case of column also, compression member also, when the rolled section do not furnish the sectional area required. That means if the sectional area that is required for the taking the higher amount of load, then we need to provide a large shape. So large shape, there is a large radius of gyration is required for, and that's why there comes the importance of the built-up columns. Now, the built-up columns, in case of the built-up columns for economical design, heavily loaded long columns, the least radius of gyration is increased. The least radius of gyration is increased to achieve this increase so that it can take the higher amount of load. To achieve this condition, two type of system are provided to combine two members to act as a column. In general, to combine two members to act as a column, various systems are provided. In general, the two systems that are provided are the lacing systems and the Batten system. Now, in our picture that I have drawn in the note, you can see this is the lacing system and this is the Batten system. In the lacing system, you can see the lacing bars are the flat bars which are placed as an angular position, and a tight plate is provided at the top and as well as at the bottom. In the Batten plate, Batten plates are provided at intermediate and at certain spacings. The plate at the end are called the end batten and the center are called the intermediate batten. So there are the two type of combined system which is provided for the built-up column section. The lacing and the battens are the load carrying element. Their function is to primarily the lacing and the battens are generally not load carrying element. Their primary function, what is the primary function? To hold the member to stay at the position. In normal RCC design, what is the role of a tie beam? Tie beam is placed so that the column are placed at the column are generally situated at their required position. In case of the lacing and batten, the work is same. In case of the lacing, in case of the batten, their basic work is to hold the members that are connected together to stay their required position. Now, if you need to see more examples of lacing and batten, you can see from figure 10 and figure 11 of IS 800. This is the figure 10. In figure 10, you can see single lacing system and you can see double lacing system. Single lacing system is used also and double lacing system is used also. In case of there is another lacing system where double lacing system and single lacing system along with cross members are used. Okay, this is the normal of lacing system. And if you want to see the batten system, there are certain, this is the batten system. This is the batten system where these are all intermediate batten plates. Okay, no end batten plates are shown here. They are the intermediate batten plates. Okay, so lacing plates and batten plates which are used to combine the members to act as a built-up column. So today we will be discussing about the design, what is the lacing about the lacing system and how to design the lacing system. So coming to the design procedure of the lacing system. Now the lacing system, in generally a flat member. In the picture you can see they are generally flat members. Flat plates are generally used. Sometimes angles sections are also generally used as the lacing members. What is the basic purpose of the lacing? I have told you the basic purpose of the lacing or the batten is to hold the members at their required position so that they do not move from the required position. Okay, and to equalize the stress distribution between the various parts. This is the basic work of the lacing system. Now, when we are to design the lacing system, we have to design the total column as a whole. So the column as well as the lacing system as a combined, we need to design. So the design procedure is very much rigorous and very much complex. So huge numbers of steps that I have told you in the earlier classes, in your theory classes, in the theory classes, I have told you that the number of the steps in the lacing design is very much higher. So we need to go through all the steps to conclude that. Okay, so coming to the design steps. Okay, coming to the design steps. Now, first design step, first we have to design the, we have to check for the section, we have to assume the column section, then we have to go for the lacing. So first, a design compressive stress is assumed. This is the first procedure in the normal column design. Also a design compressive stress is assumed. In case of the lacing design, a compressive stress is region of 125 to 175 MPa is assumed. This is the compressive stress that is assumed for Fy is equal to 250 MPa only. If the Fy value changes from 250 MPa, then we have to modify the value of the trial value of the compressive stress accordingly. Then this is the first step. The required second step is the required cross section area that we know is the Pu by the assumed compressive stress. That is the normal, like the normal column design. Then a suitable trial section now a suitable trial section has to be adopted. Now, if it is a built up column, then more than one member has to be taken. Now, if the members may be two angles, two channels, or four angles, two channels, or two eye sections. They are the sections that are generally used. Okay, if you see in my picture in the bottom part, this is some of the section that I have used. This is a angles back to back, this is the angle toe to toe, this is the angle back to back, and this is the fourth angles, this is the channel back to back, this is the channel back to back, this is the channel toe to toe, two channel toe to toe, and this is four angle back are connected. So this is a combined system of a built-up column. So the members are selected based on these cases from IS handbook. This is number 3 step. Now number 4 step, this is a very important step, because why the built-up column are provided? To increase the radius of the gyration. Now, as per the clause 7.6.1.1, the radius of the gyration, it is specified here, the radius of the gyration about the axis perpendicular to the plane of lacing not less than the radius of the gyration about the axis parallel to the plane. Consider this is a lacing bar that is provided. This is the axis perpendicular, this is the axis parallel. Consider this is the y-axis, and consider this is the z-axis. So it has been said here that the radius of the gyration in the y direction, that is the perpendicular direction, should be greater, should not be less. That means should be greater than the radius of gyration in the z direction. It is the basic purpose as per the IS code 7.6.1.1. That's why here in case of the lacing design, always Ry is taken greater than Rz. It as per the IS handbook, Rz may be greater than Ry, but always Ry is taken greater than the Rz. So if Rz, so Ry becomes greater than Rz, so Rz becomes the minimum radius of gyration. So there that means the Rz will be equals to R minimum. This is the very important part you need to remember when doing the math. We will take the R minimum that is equals to Rz, not Ry. Clear? Now coming to the effective length. Now as per the IS code 7.6.1.5, the effective slenderness ratio to be taken lest column shall be 1.05 times of the normal slenderness, actual maximum slenderness ratio. So we will determine the slenderness ratio, and it will be 1.05 times of the maximum slenderness ratio that has been calculated for the column, for that so as to account for the deformation effect. So to account for the deformation effect, the slenderness ratio to be 1.05 times the maximum slenderness ratio. This is the step 5. Coming to the step 6, for the elevated value of the effective slenderness ratio, the design compressive strength is determined. FCD is determined for the normal compressive strength. The design compressive strength FCD is determined for the higher value of the slenderness ratio. And along with the buckling class, we have to consider the buckling class also. For channel, for angles, the buckling class has to be taken for the buckling class, and for the normal value of the KL by R and value of Fy, we have to determine the FCD from the IS code IS 800. Then from the FCD, the design capacity of the column has been calculated. That is the normal design procedure. Up to that, this is the normal design procedure. Okay, we will calculate the value. Now coming to the design of the lacing. The lacing. Now first the angle of the inclination. Angle of the inclination of the lacing bar, as per the told by the lacing bar, angle of inclination. Lacing bars, whether in double or single, shall be inclined at an angle not less than 40, not more than 70. So always try to take our initial value. Always we have to take initial value of 45 degree we have to take. So it will be 45 degree when we are taking the angle of inclination. Now coming to the maximum spacing of lacing bar. Now how the maximum spacing of the lacing bar. Now maximum spacing of the lacing bar. First we have to calculate the maximum spacing of the lacing bar. Maximum spacing of the lacing bar A1. Now first, when we are going from that step to that step, a intermediate step has to be calculated. That is the spacing. What is the spacing of the column? Spacing of the column, we will come to that. What is the spacing of the column? Okay, then we will go. Okay, what is the spacing of the column? Now if we see a picture here, if this is a angle section, no, sorry, channel section, this is another channel section, placed back to back. This is the spacing of the both channels. This is the spacing of the both channels. Now this spacing is very much important. We have to place the channel or the members, the channel or the angle at a spacing, required spacing. That spacing we have to calculate. That spacing is generally calculated by this formula. For channel placed back to back like this, this formula is it. And for the channel placed toe to toe like that, the formula is this. The value of the CYY, that is called the center of the gravity, it is determined from SP6. It is determined from the SP6, the center of gravity. It is been given there. So the spacing of the channel, or the spacing of the, now if the angles are spaced like that, we have to determine the spacing. In the math it will be shown, okay, in the later stages. Now coming to the, now it is the spacing of the members. Now coming to the spacing of the lacing bars. What is the spacing? It is being specified as clause number 7.6.5.1. Maximum spacing of the lacing bars A1 should be such that minimum slenderness ratio of the component member A by Ry not greater than 50 or 0.7 times the most unfavorable slenderness ratio of the member as a whole, and A1 is length of the. Now how to determine the spacing of the lacing bar A1? How to determine that? We will go in this page. We will go to this page where we can determine the spacing of the lacing bar. Here we can see these two are the lacing bars which are provided here. This is one lacing bar, this is one lacing bar, this is one, this is one. These are the lacing bars provided. Now what is the spacing of the lacing bars? This is the spacing of the lacing bar A1. What is the value of the A1 that has been given? Spacing of the lacing bar, that is equals to 2 by a tan alpha for single lacing system, 2 by a tan alpha for single lacing system, and a by tan alpha for double lacing system. So we have to determine in this step, that is the step number 9, the spacing of the lacing bar A1. It should not be, component member that A1 by Ry is not greater than 50 or 0.7 times the most favorable slenderness ratio. So A1 by, so first we have to calculate the A1, then we have to calculate, we know the value of Ry, so A1 by Ry is not greater than 50, should not be greater than 50, either 50 or 0.7 times the most unfavorable slenderness ratio, that is the slenderness ratio that we have calculated. So this is the first check we have to do. This is step number 9. Coming to step number 10. Now what is the force that will be passed through the lacing? Lacing should be proportional to resistance total transverse shears Vt equals to 2.5% of the axial force. That means the Vt, the value of the Vt, will be 2 will be value of the Vt to be 2.5% of the total axial load that is provided here. Now, when this is the transverse shears acting in the lacing. Now, if we see the similar picture here, you can see this is the total transverse shears coming to the single lacing system. Now, where n, what is the value of n? What is the meaning of n? It has been specified here. N equals to 2 for 2 channels or 4 angle placed back to back. If there are 2 channels or 4 angles, this is a very important part. If there are 2 channels or 4 angles are there, the value of n will be equals to 2 always. Okay, so Vt by n will be equals to 2 for 2 channels or 4 angles. Always in your math it will be 4 angles or 2 channels only, so n equals to 2 for that cases. Now, if this is the Vt by n force that is acting here, so this force will be divided into 2 components here. If the angle of inclination is theta, so the parallel angle of inclination is theta, then in the step 9 the compressive force in the lacing bars will be equals to that 2 value, Vt by n cosec theta for single lacing and Vt by 2n cosec theta for the double lacing. So here it is single lacing, so this is the value of the compressive force in the lacing bars. This is the Vt by n cosec theta. We have to determine that what is the compressive force for the lacing bars. This is the compressive force for the lacing bars. Okay, clear? Now coming to the compressing force of the lacing bars. This part is as per the this code. This is 7.66.1 to at least 2.5% of the axial force in the member. Okay, so this is the value of the compressive force that acts on the member. Now coming to step number 12. Now the section of the lacing bars is initially assumed and checked for safety. Now we have to assume now coming to the design of the lacing bar. How to design the lacing bars? The section of the lacing bar has to be assumed. The width, the thickness and the spacing, and the width, the thickness and the spacing between the 2 members, that we have to, the distance between the 2 members that we have to assume. Okay, now coming to the thing. Now as per the IS code, the width of the lacing bar, the minimum width of the lacing bar shall be 3 times the nominal diameter of the end bolt. It is been specified as 3 into nominal diameter of the end bolt. This shall not be less than. So this is the minimum value. We have to take some higher value than that. 3 into normal diameter of the end bolt. Coming to the thickness of the lacing bar. Thickness of the lacing bar will be equals to 1/6 of the effective length of the double lacing and 1/40th of the effective length of the single lacing. So for a single lacing system, the thickness of the lacing bar 1/40th of its effective length, and for double lacing system the thickness should not be less than 1/60th of its effective length. Now what is the effective length of a lacing bar? Now when we can determine the effective length of a lacing bar, then comes this part, the effective length. For a single lacing system, effective length equals to, for a single lacing system, the effective length equals to A by sine alpha, and for double lacing system, effective length equals to 0.7 into A by sine alpha. This is the effective length of the column. This is the effective length of the column, L effective. That is the length of the column. So if this angle is theta, then we can determine the value of the L from here also. So L by sine theta for single lacing system and double lacing system. So when we are calculating the thickness, the thickness of the lacing bar will be should not be less than 1/40 if for single lacing system and 1/60 of a double lacing system. Clear? So this is the thickness of the lacing bar. Now coming to the spacing. The spacing of the lacing bar that I have discussed earlier. The spacing of the lacing bar is equal to 2a by tan theta and a by tan theta. Now A equals to the distance between the bolt center from here to here. Now A equals to S plus 2G in this case. Okay, now S is the spacing of the two members that we have discussed by the formula, and G equals to the gauge distance. It is calculated from the IS handbook. The G is the gauge distance. It is calculated from the IS handbook. Now there are some variability. If a channel placed toe to toe, this is the gauge distance and this is the A, so A will be equals to S minus 2G. Very much important. If channel placed back to back, A equals to S plus 2G, and if there are four angles like this, if this is the gauge distance, so A is equal to S minus 2G. So these formulas has to be remembered for every case. So this is the value of A. We need the value of A to determine the spacing of the lacing bar. We need the value. So this is the clause number 12. Okay, the step number 12. Here we are assuming determining the design of the lacing bar, the width, the thickness and the spacing of the lacing bar we are determining. Now coming to the step number 13. Step number 13 is the minimum radius of gyration. Minimum radius of gyration, minimum least radius of gyration here. Now the effective minimum radius of gyration of the lacing bar should be, R minimum should be T is equal T by T into root 12. This is the minimum radius of gyration that we have to calculate it. Now coming to step number 14. Here we have to check for the effective length. I have already discussed what is the effective length of the of a lacing bar. As per clause 7.6.6.3, here also it has been specified the length between the inner end fasteners of the bars and single lacing and 0.7 times this distance length for the double lacings. So this is the values for the single effective length for the single lacing system and for double lacing system. Now comes the slenderness ratio. So R minimum we have calculated. This is the value of the R minimum. Now L affected by R minimum should be less than 145 as per the code number, clause number should not exceed 145 as per clause number 7.6.6.3. So this is the value of the slenderness ratio. This is the step number 14. Now coming to the step number 15. The design compressive strength of the lacing flat is computed for the calculated value of the lacing flat. This should be more than the force in the design compressive strength of the lacing flat. The design compressive strength of the lacing flat is calculated, and step number 16, the design tensile strength of the flat is calculated. Now how to do that? How to calculate the design compressive strength and the design tensile strength? Now this should be more than the force in the flat. We have what is the force in the what is the actual compressive force in the lacing flat that we have calculated from here. This is the Vt by n cos theta for single lacing and Vt by 2n cos theta for double lacing system. So the compressive strength of the lacing bar should be more than that. How to calculate the compressive strength? E to E based on that. Now the compressive strength of the lacing flat is calculated PD into FCD by AE. The compressive strength of the lacing flat is calculated by the procedure as the column PD into FCD by C. That is the FCD and AE, where FCD is for L effective by R minimum. So FCD in that case will be calculated for the L effective by R minimum. That value we have calculated, and the FCD will be based on that. And AE will be the area of the lacing flat. This will be the value of AE. Okay, we know the value of L, we know the value of L, and we know the value of the width of the lacing bar. So L into B will be the area of the lacing bar. So FCD into AE will be the design compressive strength. For the tensile strength, the tensile strength should be minimum of the tension. It will be designed as per the tension member design that we have discussed, that TDG is equal to AG. This is the cross section yielding, this is the net section rupture for both welding and bolted, for both only for bolted, because net section is only for bolted connection, because welded connection only the cross section is taken. So in between, which is the lesser value has to be taken. This is the tensile strength should be minimum of these two values. So we have to calculate tensile strength. It should be greater than the force in the lacing bar, the Vt by n cos theta and Vt by 2n cosec theta. This is the force in the lacing bar we have calculated. And the last is that then comes the issue number 17, where the design of the connection. Now the lacing bars should be connected with the lacing bar should be connected with bolted or riveted connection or welded connection. So the design of the connection has to be done. The strength of the bolt should be more than the load carrying to the rivet. The strength of the bolt has to be calculated by shear, and by strength of the bolt in shear, strength of the bolt in shear, strength of the bolt in bearing, that we have also that we know how to calculate. Then the lesser than that we have to calculate. Then we have to calculate this should be the bearing strength, and the should be if the two lacing bars are connected the same. Now there comes another important part. This is the thing: if two lacing bars are connected at the same point like this, if the two lacing bars are connected at the same point like this, the load coming to the bolt or rivet will be equal to that 2 into Vt by n cot theta. And if the two lacing bars are connected at different point like this, the force in the rivet or bolt will be Vt by n cosec theta. So this value is for two lacing bars are connected at single point, and two lacing bars are connected at the different point, the value will be Vt by n cosec theta. So the force in the lacing bar, the force coming in the lacing, coming to the bolt or rivet in the lacing will be that. So the design of the bolt, the number of the bolts will be calculated by this value. This is the value. The number of the bolts will be calculated by this value divided by the strength in the lesser value of this strength in shear or bearing. Okay, then the number of the bolts will be calculated. Now coming to the welded. For welded connection should be provided along each side of the lacing bar for full length of the lap. The overlap should not, this is the main important part, the overlap should not be less than 4 times the thickness of the bar. So thickness of the bar we are providing, the length overlap should not be less than 4 times. Now coming to the last step, this is the last but not the least, the column ends are tied with tie plates. In the lacing design, in the lacing member, what we have discussed, this is the tie plate. So when we are in the tie plate, when we are designing the tie plate will be designed as per the batten plates, because tie plate is a batten plate like the end battens. The end batten plate, the tie plate will be designed as per the end batten plate. So to complete the design, to complete the lacing member design, we need also idea about batten design. In the next lecture we will be discussing about how to design the batten plates. If we combine the lacing and the batten, then we can design the both lacing and the batten at the same time. Okay, so in the next class we will be discussing about another type of built-up column system, that is the batten plate system. So up to that it is for today. Okay, do the assignment and submit it, and thank you very much for your time, students.